Welcome to our webinar for Chemistry in the Community, the 6th edition, on Unit 5, which is Industry Applying Chemical Reactions. Tonight we have with us Steve Long, who is from Arkansas, Cece Schwensen from California, and Barbara Sitzman from California. All three of them are experienced high school teachers that have been using chemistry in the community in their classrooms. And they're going to walk through all of Unit 5 with you tonight. I'm Michael Murray, and I will serve as your tour guide as well. So here we start with Unit 5. This is the opener page, and it tells you what the students are going to look at. In Section A and B, students are going to look at nitrogen chemistry and look at fertilizers and agriculture and the production of ammonia. In Section C and D, we'll switch gears and actually look at batteries and electrochemistry. So we're actually looking at two different industries throughout this unit. So the unit opener is actually has students deciding whether they should have Company Y or Company X come to Riverwood. X is a nitrogen products company and Y is a battery technology company. So students will weigh whether either one of those companies or neither of those companies should come to the town of Riverwood, and they'll end the unit with doing another town council, such as the one that they just did in Unit 4 in the water unit. They will do that to decide which company based on what they learn in this unit. So I'm going to switch it over now to Steve, and he is going to go through Section A with you. Welcome, Steve.
Thank you. In Section A, we're going to be concentrating on the role that nitrogen chemistry plays in agriculture. And the goals are listed in your book. And they are to look at the ingredients that are found in fertilizer and to investigate typical fertilizers on plant, look at the nitrogen cycle, which is, of course, an important part. And the chemistry comes in really strongly here with the electronegativity trends upon elements. This is a unique approach to using electronegativity. I haven't seen other sources use this, so I think this is a nice touch. And then, of course, we have to look at some bonding in terms of covalent bonding and electronegativities and things of that type as we work through that. So this sets a nice piece for understanding something about the role of chemistry in agriculture. And everybody likes food, so this is a good way to tie some of this in. The concept checks, you're probably familiar with these from previous webinars or use of the book. And students would go through these. They take a look at things moving forward and some things moving backward, and cause students just to pause and reflect a little bit, kind of a self-assessment of what's taking place and going on. We're going to link in the concept in this back to previous cycles that we've done, and so you notice that the carbon cycle and the water cycle have been mentioned, and so as we come into the nitrogen cycle, that'll be a nice piece to come back around. Then as we move into the first activity, we start off with a fertilizer components investigating matter. This is a very complex lab that students would do, and this is a full-scale qualitative analysis lab that students would work with from this. They should have gained some experience out of their water unit previously, so the skills should be there to be able to do this. They're going to be taking a look at some ammonia. They're going to be doing qualitative tests, and as the slide shows, you'll be taking a look at for the barium chloride test, the brown ring, the sodium hydroxide using litmus. They'll do a flame test. I believe this is the only flame test in the material this year, isn't it?
Yes.
Cece? Yeah.
Yes. Yes.
That's right. Yeah, the only flame test. So if flame test is a part of curriculum, this would be an important lab for you to do. And also then the thiocyanate test that would go on there for the iron as well. Then they get to do an unknown, and that's always interesting for students to be able to take their skills and apply it to an unknown process that they have going on. This lab takes a lot of time to set up. I won't lie to you on this. So when you set it up, you might plan for quite a bit of time in advance, but the nice thing is that much of your preparation then can be saved. It can be kept in pipettes or other dropper bottles and stuff and used from year to year across the process with that. You'll also need cobalt glass squares for doing the potassium ion flame test. And you should make a note that your iron 2 sulfate solution for the brown ring test needs to be very fresh. So make sure that that's not something that you store, but that you fix that up each year. I have a little bit of problems setting out concentrated sulfuric acid just from a safety standpoint. And so you may either want to dispense this on your own, or maybe do it as a demonstration for students to be able to see. But that's something that you would obviously work with the level of students and the safety that you have in your lab and the confidence that you have in your student skills. So it's a complex lab, but it's a very good lab. It teaches a lot of chemistry, and once you get it set, it can be used from year to year back again. Then we move into A2, which is taking a look at fertilizer and the nitrogen cycle. And as we mentioned earlier, students have already looked at the water cycle and they've looked at the carbon cycle. And so now they're going to be taking a look at extending this knowledge to the nitrogen cycle. And this is a very complex cycle. It's not quite like a three-step water cycle process. It's a much more complex process. And I find that my students have some amount of difficulty internalizing this. So you may need to spend a bit of extra time on that. As you read through this, they'll explain the steps of the nitrogen cycle, and this will provide some information for a modeling matter that will come up a little bit later on down the line. In A3, they're doing a making decisions activity where the students are having to look at the benefits of fertilizing versus what the negative impact might be by over-fertilizing. And perhaps in your area, like in my area in Arkansas, there's a lot of concern about waste nutrients running into the water systems and getting into lakes and streams and causing algae blooms and other types of processes. So you have to take a look at the cost benefit of what is the value of using the fertilizer versus what the detriments to that might be, and then also take a look at why farmers would want to use it. Is there a way to perhaps use less and still get the same benefit? Mm-hmm. So a good discussion that takes place here as they come through that. We're into A4. Here's the nitrogen cycle that pops up. Let me caution you that while the title talks about the nitrogen cycle, please note that the figure is for a carbon cycle. And I have a lot of students who want to just jump right over to that picture, and when they start discussing and drawing and working on their own nitrogen cycle, they just duplicate this picture because they don't read the caption that said, this is the carbon cycle. So make sure that they don't make that crucial mistake and that they understand the difference in this. So this is just a model of what a cycle would look like and how they might kind of work through that process again. So our next set of concept checks here, taking a look at the similarities of the carbon and the water cycle and what might be different. We know that when students do similarities and differences, that's one of the greatest benefits that they get in terms of their own learning. So this is a nice way to have them analyze that. Looking ahead for substance to be oxidized and to take a look at covalent bonding. So again, looking back a little and looking forward a little is the really nice thing on these concept checks. As we move into the next part, we're taking a look at fixing nitrogen by oxidation reduction. And in this part, they're reminded a little bit about the Haber-Bosch process. This is a unique way of taking a look at fixing nitrogen. And students are going to work with the electronegativities and the charts given there. They're reviewing back to some oxidation reduction that they're doing and some oxidation states that they've looked at. So you might want to have them analyze for the trends of electronegativity. That would be an important periodic property for them to do. And also to think about a little bit of the electron dot structures that they have done and to relate that to this oxidation reduction process that's going on. In A6, this is when they're developing some skills. They're looking at some problems. They're using these electronegativities from the previous chart, and they're making some predictions about which element would be the more positive and which would be the more negative, and then using that to be able to make some predictions about the elements. Please note that they don't necessarily have to use the oxidation numbers that are here. They're just trying to use electronegativity values to say this element would be more likely to gain electrons or this one would be more likely to lose. And therefore, which one would be more likely to have a greater pull in the formation of the covalent bonds that would be formed. And that's a rather unique approach to introducing electronegativity and working with oxidation states. And I find that the students really do quite well with that. A7, we're taking a look at, as students are going to read in A7, they're going to read about the products of the chemical industry. While students are aware that chemistry is involved in their lives, I don't think they're ever really very highly aware of how many different aspects of their lives that the chemical industry includes. And of course, if you look at petrochemicals, as well as the pharmaceutical industries, and then all of the different types of things that would come into play, they can see that chemistry has a major role in their life, everything from paints and sports equipment to the plastics and the foods and the medicines and stuff that we use. And so these pictures just represent some of the ways that products are used in the chemical industry. And then last we finish up on part 8. And so this is going to be a making decision to take a look at how students would begin to use some of this information to focus on their final project, and that is their town council meeting, where they're going to decide whether to invite the fertilizer company or the battery company into their town to take a look at this. And so this would be a very critical activity for your students to do to be successful in the putting it all together activity at the end of this unit. And I think that kind of concludes my section then. Once again, we kind of summarize with what's taking place here, that fertilizer is necessary for growth and that nitrogen is transformed chemically through systems. They've talked about electronegativities and the ability of electrons to attract themselves to a bond. Taking a look at oxidation states, either being positive or negative, being either an oxidation process or reduction, and how the chemical industry is very important in transforming things around us into ways that make our lives very useful and very productive in a lot of different ways. So as they continue through the summary, just taking a look at how nitrogen plays a role in agriculture, and that just follows up to the beginning question that we opened up with to start with here. And I think now I turn the program over to Barbara.
Right, hello everyone, and this is section B, and the major goals here are we're going to be looking at kinetics and equilibrium, and they're introduced in the context of the production of ammonia. So students are going to be applying Le Chatelier's principle in order to learn ways to maximize the production of industrial products. As you note from the goals, they're first going to be looking at the factors which affect reaction rates, and then we'll be moving down and really stressing the idea of the dynamics of an equilibrium. They will be studying equilibrium in a qualitative sense in this section in the lab work that they do that we'll look at a little bit later on. And then when we get down to the reason that my students have enrolled in chemistry, or that they like to think that chemistry is going to be fun, is we get to explosives. We take a look at that. And then they do well introduce green chemistry in this section. This first concept check, they've seen the double arrows briefly before in the text, and so they're asked to recall and see if they remember what the meaning of this is. And in number 2, I think that this one's important. I don't assign all of the concept checks for them to do, but number 2 is one I would assign, because they've studied the kinetic molecular theory in the 3rd unit. So, no, excuse me, in the 2nd unit. So they know that pretty well, and they should be able to remember and apply that. And then number 3 is really a terrific one that asks them to look at the dynamics of an equilibrium. Here students will review the path of a chemical reaction. This was first introduced in the second unit. The reactions and products of the Haber process are shown in the potential energy diagram. The collision theory, the function of a catalyst are reviewed, and then equilibrium is introduced with emphasis on the dynamic quality of the interaction between reactants and products at the particle level. You notice the reactants and products are the reviewing, trying to picture things at that particle level. This is one of the Scientific American pictures that is so excellent in helping, again, students look back at this particle level. And so they take a look at the difference between, with the little particles, at the difference between a true equilibrium on the left, and then on the right, what happens if you take that stopper off and you have, you no longer have a closed system, you have just a steady state where there is continuous evaporation and not very much going back into the liquid. This is the lab that I mentioned earlier in the goals, and there are a few twists on this from the standard labs. It's a much greener lab than has been used before. It's quite an improvement over the standard cobalt water complex and cobalt chloride equilibrium. For example, sodium chloride is used to provide the chloride ions rather than hydrochloric acid. Temperature is also investigated, and silver nitrate is used to precipitate the chloride as silver chloride. By the way, I always keep a bottle of spray and wash on hand because it does a nice job of chelating the silver ions to prevent stains if students spray their hands. They just spray their hands and then wash them off after the lab. The next slide is the developing skills on equilibrium, on Le Chatelier's principle, and this is where students test their understanding. The graph shows the direct relationship between the mass of ammonia gas at various temperatures as a function of the pressure in the production of ammonia. And they have several different questions that they answer that test their understanding of the stresses, the effect of the stresses on the equilibrium. And in B4, they take a look at the industrial synthesis of ammonia, and the caption under the photo, which isn't shown right here, asks the students to take a look at the safety precautions that are used not only in their lab, but in the industrial industry. And there's some nice marginal notes for the teacher that in this section that help the teacher guide the students through some of the history and further explanation of the Haber-Bosch process. And now we come to explosions. Students will read this section. I found that they're very, very interested in TNT, nitroglycerin, and an explanation of explosions. And here again, we're bringing back the information that they learned about the formation of gases and the amount of volume that gases take up. They learned this in the second unit, in the air unit. And the reading in this section brings in the process of inflating airbags, which is quite relevant to them, and emphasizes the explosive power of reactions that produce large number of gaseous products. The history of Nobel and the events leading to the Peace Prize are covered in this section. In this developing skills, they're given, if you notice, the sample problem uses dimensional analysis and shows them how to use the balanced equation, the stoichiometry, to figure out the moles of the carbon monoxide that are formed. And this is really a good exercise in just simply stoichiometry and problem solving. And if your state tests are anything like ours are currently, there is lots of stoic on them. So I make certain that I've gone over this material before they take their tests in the spring. I think next we have concept check. 1 and 2 are really a good review of the equilibrium principle, and showing in number 2 the steady state, and how that is not a violation of Le Chatelier's principle. I often just turn on the water at the water faucet in the classroom and ask students if this is an equilibrium, and if not, why isn't it an equilibrium? What would we have to do to make this an equilibrium? And number 3 is asking them to begin looking at these 2 companies and starting to build on what they learned in section A toward looking at their PIOT and the thermodynamics involved in it. In sections 7 and 8, section 7 is a reading section, and there are green chemistry icons on the margin that highlight the EPA cleanup of chemical waste sites and the importance of, in green chemistry, of trying to reduce the waste products, such as using the caffeine that's removed from coffee, and that can be used to decaffeinate energy drinks and so forth. They give quite a few examples of that. And they also list the 4 important factors: engineering, profitability, waste, and safety, that are important in large-scale chemical manufacturing. In section 8, students are asked to consider the energy requirements involved in producing ammonia, as well as processing and the production of the starting materials. And here in section 9, they actually list the green chemistry principles, the 12 principles. And actually, if you contact EPA, I've done this. They're very nice about sending you a class set of bookmarks that have these green chemistry principles on them. So I have those that I give to my students. This is basically technology designed to reduce the amount of hazardous substances that are produced. Then we have in B10, this is the activity that provides the beginning information for the final project. My students work in groups and begin to identify the relevant arguments and strategies for the town meeting. I found that since the students are working in groups, that I keep all of the papers that they use along the way as they're doing these pre-project activities and so forth. I have a little box with their group numbers in them, and I just keep these filed, because otherwise everyone gets to work and they want to look back on something, and the person who happens to have the paper that the group worked on is absent that day. So I just keep them all together, and the kids know, and they go up and they pick out their papers and they can look back through them, and this gives them a lot of background to work with. And in the B summary, this slide shows the heading for the section summary questions. And I don't assign all of the questions to do, but this is really a pretty good guide for me, so that I can assign questions usually 2 to 3 sets during the course of studying a section, and I assign the ones that are relevant to the material that we have gone over at the time. I find it's easier than for them, and it's a bit of feedback right after they've been studying the sections than to wait until the end. There is always, in each one of the section summaries, there is a green banded question. I use this as a prompt because my students keep composition books, and the final thing they have to do at the end of each section is to write their own reflection of the section. And I ask them to look at this green banded section to use as kind of a prompt. They can certainly add more things to their reflection, but this gives them a good guideline for the things that were most important in the section. So I think it's going on to CC now.
Yes, CC is going to
Okay,
be
so for section C, we start to look at the other industry, which is going to be a battery production plant. And we start by looking at electrical energy being generated from chemical reactions, and the goals include looking at a voltaic cell. They will actually do some exploration in an investigating matter of that. They'll use the activity series that was introduced in Unit 1 and some other information to predict which direction the electrons flow. They are going to use illustrations and make their own illustrations describing the oxidation reduction reactions that occur in those voltaic cells. And then finally, they're going to go back and revisit the concept of equilibrium and spontaneity and how those affect voltaic cells. I think that in many cases, electrochemistry is intimidating to teachers. There's a great deal of teacher background support in your TE around the edges. Read that, and I think you'll feel much more comfortable. In the first concept check, students are, in concept check 5 now, students are looking at oxidation and reduction, a concept that was first introduced to them in Unit 1 and then addressed a little bit in Section A when we talked about electronegativity. The metal activity series, again in Unit 1, I think it was on page 75 at the very beginning of the year. And then the forward-looking question really does give you some indication of how students are thinking about that, the energy and a voltaic cell, and what, how we might be measuring that energy. Then we go on to section C1, and we look at that activity series. It's slightly different than the activity series that was on page 75, where we simply had the element and then the ion that was found in the minerals and how we might process it. Now we're really looking at the element, and we're looking at them as reduction reactions. And so you have the ions that are formed and the number of electrons that are generated. The other diagram is one that they'll get very used to, and that is the diagram of a relatively basic voltaic cell, where you have the copper electrode in the copper-containing solution, copper sulfate. You have a salt bridge, you have the solution of zinc sulfate and the zinc electrode. And as long as the wire is there and the salt bridge is there, the electrons will flow. And they know, or they should recall, which of those two metals is more reactive by looking at the activity series, seeing that zinc is above the copper on the activity series indicates that zinc is a more reactive or more active metal, and so that one would be the one that would tend to give up the electrons. Then we go on to investigating matter C2, and this one is structured slightly different than some of the other investigating matters. Here, in the preparing to investigate, they're actually in the lab working through and setting up a voltaic cell to help them ultimately ask questions. Now, this cell sort of looks like a complex thing. It's simply a piece of filter paper cut with 5, you could use 4 if you only had 4 metals, 4 arms, and each metal piece is placed on an arm. The metal ion solution is what keeps the metal in contact with the filter paper, and then you have the salt bridge or the potassium nitrate in the center that you're dropping out, and so the filter paper gets damp, but you don't have puddles of water in between it. And then you're using a voltmeter, your multimeter, if you have interface, any sort of technology, you can measure the differential between the metals. And so this is a great place to use your probes, but if you don't have those, a simple multimeter from Radio Shack is sufficient. And you will help guide students through setting this up, and once they have it and they've seen how to measure, then they're going to generate some questions and develop a procedure to answer those questions. And we have some for you to kind of prompt, and I will often find students need a little bit of guidance in what might be a question that would be useful. A tip that is in the TE and that I found incredibly useful was to cut your metals in different shapes. You can reuse metal from year to year, and if you have them cut in different shapes, it's much easier to put them back so you have the zinc with the zinc and the aluminum with the aluminum and the tin with the tin. When they're doing this at the end, you're having them look at the activity series and to start to analyze what the half reactions are and which element is being oxidized and which one is being reduced. Then we go on to section C3, and students are now being asked to analyze voltaic cells and half reactions. So they are looking at which electrons or which elements are giving up electrons and which ones are taking them on so that the electrons can flow and generate that electricity. And then there are a couple of mnemonics. The oil rig at the very beginning, the oxidation is losing electrons, reduction is gaining, and then the red cat, reduction always occurs at the cathode. And this is a half reaction that they initially started in a modeling matter in Unit 1. Then we do a developing skills. Oh, wait a minute. We have the chem quandary where they're looking at whether fuel cells or energy cells are created equally. And this is a time when students can start to bring in what they know about their cell phone batteries, car batteries, fuel cells from other places, and we can start to talk about whether they are all equal and what makes them different. What's the difference between the battery that you use in a flashlight and the battery that's in your computer? And then we go on to developing skills where they are actually measuring and drawing voltaic cells they're predicting the direction of the electron flow, they're writing the half reactions, they are looking at which metal would be the anode and which metal would be the cathode, and they go through that with a series of half reactions. Many of them are reactions that they actually measured in their voltaic cell that they did in the investigating matter in C1. Then we get to the concept check number 6, and we look at what happens if a salt bridge is missing from the voltaic cell. We look at, students are being asked to think about the things that they learned in the first part of this unit, and as well as what they did in the investigating matter and the diagrams that they've drawn, and try to recall that. The second one is trying to get them to think about all of the questions that they and their classmates have asked. And then the third one is having them start to think about what they learned in Section B about equilibrium and how that might apply to a voltaic cell. And is it desirable to have a voltaic cell at equilibrium or not? Once they've done that, there's Section C5 is a reading section that has them going back to talk about the equilibrium. We're looking at spontaneity, and students are often surprised to find that a reaction is occurring spontaneously, but if it gets closer to equilibrium, the reaction is not going to go. And so then we talk a little bit about electrolysis and how putting energy in will cause the reaction to go in the reverse reaction, or in the reverse direction. Then we are asking students to do a modeling matter. In this modeling matter, students are sketching voltaic cells. They are looking at where the electrons go. One student of mine who clearly had too much time on his hands made a little flip book of all of the electrons moving through. It was a lovely little animation that I stole and now use all the time. They are being asked to visualize what is going on at the anode and at the cathode. This is really easy for some students and very difficult for others. Some students can visualize the cells as from the particulate nature, and some of them are not there yet. But I think that having them work through it, and this is a time where I partner them and try to get the abstract thinker and the students that can visualize particulate nature with students who are much more concrete and are having difficulties. And then we end that unit by looking at industry or company Y. We start to think about those principles of green chemistry and what sorts of things might be of concern for us in this town of Riverwood, and as we're going to put our town council together, what things are important for the city to think about. And then we are on to the section summary questions. In the section summary questions, they're the boxes that group all of the ideas or all the questions together are on this slide here. And as Barbara said, she assigns them at units, sections at a time. I do the same, and I follow to some degree the planning guide that's at the beginning of the section in terms of trying to assign summary questions when the students have studied the topic. And then last but not least, we end with revisiting the section question and asking students to reflect using some terminology that they may or may not be familiar with. And the equilibrium one, they absolutely are, but seeing how they can tie that to the section question. All right. The chemistry at work, this is really fascinating for students. They start to look at the differences in batteries. This one is a place where a KWL comes in. There are lots of things that students think they know. There are lots of things that they want to know, and then there are a great number of things that they learn in this two-page interaction with the material scientist, but also some things that they will continue to learn when they go into Section D and the industrial production of batteries. All right, so Section D, we're starting to look at batteries. Here are the objectives, the goals. The question we are trying to look at is what challenges we have in production and use of batteries. There are there's some information about primary and secondary batteries, a term that students probably have never heard. They will actually calculate, they'll make and calculate how much potential they'd have in a voltaic pile, and then they'll look at the life cycle of the battery, and they'll use the burden-benefit analysis and try to decide which of these chemical industries might be beneficial to the town of Riverwood. Right, the concept check, number 7, we're looking at the first question, which was answered at the very beginning of our Section C. You're looking at the investigating matter and seeing if they remember what the answers to those questions that they asked in the investigation might be. And then number 3 is looking forward, but it's also trying to mine some of the information that students have. Some of your students will have a lot of information about batteries, especially as they're using more and more battery-powered devices. In Section D1, investigating matter, the students are going to do something that's actually sort of historic. They are making a voltapile, or a voltaic pile. What's happening here is you have a copper piece, and the white is a piece of filter paper or blotter paper, and then the silver grayish pieces are zinc. So you have, in this picture, you have 4 separate cells. And so what the students do is they're all cut the same size. The blotter paper is damp but not wet, because if you have water or solution bleeding from one side to the other, you short it out. It's a little bit challenging to make the first time, but once students have done it once, it gets a little bit easier. If you have machine shop, or if you have someone who can die cut the pieces, if they're all cut in uniform size, that makes things much easier. The other suggestion in the lab itself, it says to use copper sulfate solution. Any salt will work, so sodium chloride, potassium chloride, potassium nitrate, any of those will work as your salt bridge. And if you use something other than copper, if you use a potassium or a sodium salt, it makes cleanup and reuse much easier because you don't have the spontaneous oxidation reduction between the copper sulfate and the zinc, so you don't have that cleanup. Students will measure or predict how many piles they need, and you can actually get the students to power a small battery-operated device, a little motor, spin a motor, a little wind turbine, something like that. And they're, you know, even as simple as lighting a light, and students are thrilled that they were able to actually get it to generate enough electricity that it could power this object. In section D2, students are being asked to use the standard reduction table. Now it's added one more thing. We not only have the half reactions, but now we have the electrode potentials measured, and so they can now start to see how reactive and non-reactive metals compare in the standard reduction potential. And in D3, we use that information in calculating the potential in electrochemical cells. So students are using the table and they are looking at a variety of different metal combinations, and they are measuring the cell potential across those cells. In section D4, we are looking at what a primary battery looks like. A primary battery is a one-use battery, a typical dry cell or alkaline battery. The diagram here has all of the parts. I have never had kids cut them apart, and it's not something that I would recommend that they do, but there are lots of diagrams out there for students to look at. This is a reading section. I generally sort of read and discuss this as we go along so that we can compare what's happening oxidation reduction wise for a zinc carbon battery and then for the alkali battery. We get into the chem quandary, and we're looking at what it means for different batteries, different sizes, why one would use a really large battery and a small battery, and what it means in terms of hours and all of that. And this is a really lively discussion for students, but at the end of the day, they all want the answer. They all want to figure out, you know, what the right answer is. So often I send them out to do a little more investigation on their own. In section D5, we're looking at the secondary batteries. Secondary batteries are generally nickel-based. They're rechargeable batteries, but also the lead acid batteries in a car are secondary batteries, and more common, all of the lithium-ion batteries that power laptops and their iPad and all of those other kinds of things. Again, this is a reading section with some diagrams. This is one that I will have students read and we'll discuss in class. It's not something that I'm going to let them send them home, because many of them will come back and have read it and really understand it, and others it will have looked like they were reading a foreign language. In section D, or before section D6, we do another concept check. We're asking the Scientific American, sorry about that. Scientific American working diagram is fabulous in terms of showing students the cross-section of a battery, sort of what's happening there, and then it explains the chemistry below as well. These are really well done and are a wonderful addition to that section. Right, we get on to the concept check. Students are being asked to look back and compare or to distinguish between primary and secondary batteries. They look at lithium and lithium-ion cells, and then they're looking forward to recycling and thinking about the life cycle of batteries. Many of the students are aware that they shouldn't go into a landfill, but they don't necessarily understand why, and this is an interesting disaggregator for students to see where they are in terms of understanding the keys to recycling. In D6, we get the manufacturing and recycling of batteries. We start to look at the life cycle. This is another reading section that is asking students to look at the life cycle. They're looking at manufacturing versus recycling and what that looks like. When we get to that table, for whatever reason, that table is really hard for students to figure out. So I spend some time talking about what's happening in each one of those tables, or in each one of those sections. In D7, we are doing a modeling matter. Students are asked to look at the life cycle of the battery. They are, again, trying to come up with the steps for what would have to happen and explaining how much energy is needed, what the wastes are, etc. This is something that students really respond well to, at least in my experience. It's starting to think about why recycling matters, and especially for things like batteries that are a limited commodity. And then in the Chem Quandary, we are looking at commodity or specialty. Students may or may not have heard the word commodity. They may or may not understand what it is. We throw it around regularly, and students don't necessarily know what it means. That leads us into the discussion in D8 about greener methods and products. We're looking at green chemistry here, really being able to look at the positive and the negative factors for green chemistry, and starting to think about the burdens and the benefits for battery production and recycling. And last but not least, we end this unit with the sort of capstone of the making decisions for the battery company. They are having to consider the burdens and the benefits of generating the batteries and what that would mean. And that prepares them to either support or refute the production of batteries in their community. And we end with the summary questions, as we have in every unit. Again, I do them a few at a time, especially after we've had a section on that was pretty complex with some reading. Here are the topics in the section itself, and then we end with the section question. In the section question, they're being asked to consider that life cycle and the green chemistry principles, and they hadn't before. And last but not least, they're preparing for their town council meeting. This is another, depending upon when you do this unit, you may end up having 2 town council meetings back to back. That doesn't seem to bother my students, but I've also had times where I've had it at a different time. And ultimately, the town council has to decide whether you're going to have the X company, the Y company, or neither. And that is that unit.
Thank you, Steve, Barbara, and DC. At this time, if anybody has any questions, you may type them into the box, and I will read them for our speakers to share or to answer. And thank you for participating in the webinar as well.
And I have to apologize. I have to sign off. So hopefully Steve and Barbara can answer your questions.
Thank you very, very much, CC.
All right. Take care.
Good night, CC.
Good
Good night, CC.
Does anybody have any questions? Barbara and Steve, do you have any final thoughts on the unit?
I don't believe I do. I think Cece did a very nice job of wrapping it up for us and talking about the town council meeting.
I would simply say that compared to the 5th edition, I think the 6th edition, the electrochemistry part of it, is much more engaging, and I think that has a lot more information. It's just such a nice piece. I know that the writers, including Cece, worked hard to put that information on the batteries in there, and I think it just has some really nice pieces like producing your own voltaic cells, where they produce that energy, and then for them to understand how important batteries are in our life. I mean, we live on batteries, you know, our cell phones and our computers and our cars and everything. And students, I think, really understand and appreciate the knowledge they gain in this section C and D in this piece particularly.
I definitely agree with that. Okay, we do have a question. Let me pull it up so I can see it. So, Donna, you have a question that you don't have a copy of the text. These are not the entire text pages, but like this is a part of the page from the text that is that's on the screen right now. And these are only samples of the pages. And I will ask W.H. Freeman to send you a copy of the text so that you'll be able to look through that. Any other questions? Okay, I'm going to stop the recording.